Okay, Thursday, the next homework assignment is due, and it includes a numerical integration method problem. That's problem 2. And in the in-class example, you may remember that we broke up a segment into different steps. And it doesn't say so in the problem statement that you should break it up into steps, and so you can solve it in one step if you like. But it's kind of interesting to compare how the length of the profile changes, this one quite a lot, depending on how many segments you break it up into. And so if you're interested to play around with that and see the different overall lengths that you get, I'd encourage you to have a look on that numerical integration problem. Now, problem 23 is related to the direct step method, which is what we're going to be tackling today. So the direct step method is also known as the step-by-step method. And the reason why is because we're going to be breaking up profiles into different segments and then finding the length of each one of them by accounting for the energy grade line slope at the midpoint. And so this bears some resemblances to the numerical integration method. Let's start with this, because we have to revisit the idea of total energy and where the energy is going between two sections in a channel where the depth is varying. And so remember that the water is flowing from 1 towards 2. That should be obvious by now. Water flows downhill. If you didn't learn anything else from hydraulic engineering, I hope that water flows downhill is one of those things, is the one thing. Except in Abu Dhabi, right? Okay. Okay, so let's look at relative to the horizontal. There's this segment of elevation here that's related to the slope of the channel multiplied by some distance between 1 and 2. And so delta z, in other words, is just the channel bed slope multiplied by the segment length. Okay? Y1 is the depth of flow at 1, and then there's the velocity head. And so that gives us the total energy at location 1. Now at location 2, we've picked location 2 such that it is, by definition, where our elevation datum is starting from. And so there's no delta z like there was at location 1. There's just the elevation, the velocity head, and then this is the energy loss. If this was uniform flow, then S sub f times dl would be equal to S naught times dl, because the channel slope would be equal to the slope of the energy grade line. But this is not uniform flow. That's why we're doing these water surface profile calculations, is because conditions are varying gradually. So what this equation is saying that we can account for where the energy is at location 1 compared to the components of energy at location 2. And it has those different pieces that we've just talked through. And because the two slopes aren't equal, then that means that these two elevations, the excess bed elevation at 1 and the energy loss at 2, aren't equal either. So we have to keep them separately. And when we do that in the direct step method, the slope of the energy grade line that we're going to be accounting for is the slope at the midpoint, because we're going to have to be sort of taking into account the average over some length. So let's rearrange this equation. And if we do rearrange this original energy equation, we can isolate the difference in the slopes and multiply it by the segment length. And then that is essentially the difference in the energy at 2 compared to the energy at 1. And so, like I mentioned before, the slope of the energy grade line that we're going to be using in this method is the midpoint energy grade line slope. And so then we calculate the length of a segment, how far it is between points, by calculating the difference in energy between the 2 points divided by the difference in the slope minus the average energy grade line slope. Now, there are a couple of guidelines on how we should apply this. The first is that if we have subcritical flow, then we work from a known location that is downstream and work upstream. And the reason why is that it's at upstream that we're going to be able to find the normal depth again in a subcritical flow. In the case of a supercritical flow, then typically what we'll do is start with a known depth upstream and then work downstream instead. Because of this limit that our difference in water depth should be 0.5 meters or less, then that means we have to divide a reach into several segments. And so if we know that the normal depth upstream is relatively shallow, but we have some sort of a choke downstream, then we can't go from that really deep water at the choke up to the normal depth upstream in just a single jump. We should limit it to incremental changes in a water depth of 0.5 meters or less. And so that tells us how many steps we should take. We're going to use the entirety of class today to work through this one single example. And yeah, we may finish early, I don't know. So we have a rectangular channel, which makes it a little bit easier to solve for our critical depth, since we can define the flow per unit width for a rectangular channel. Its channel slope is given 0.15%. We know the width of the channel and then the flow rate that it's carrying. So downstream, there is a broad-crested weir that's choking the flow, and they measured the depth just immediately upstream of that broad-crested weir, and the depth's 3.8. So we know it's 3.8 here, and we want to find out, first of all, what depth is it eventually going to decrease to? You know, at this point, we haven't necessarily classified the water surface profile, and so to do that, we should calculate the critical depth, the normal depth, and then you can compare the given depth of 3.8 to the critical and the normal, and then know if it's an S1, 2, 3, or an M, 1, 2, or 3. And so that's kind of a review. These first three steps are a review. After you get through that, then consider, according to the limit of 0.5 meters per segment, then how many segments should this be divided up to? This may just be for purposes of illustration. I'm not saying necessarily that there definitely are 7 segments we have to divide it up into, but based on the difference in the upstream normal depth and the downstream depth immediately before that broad-crested weir, so find out how many steps there have to be, and then what should be the depths for each one of the segments. Because when we apply this method that we're going to go through, we have to know the Y1 and the Y2 for both of them. And so you're already defining the depths, but you're just finding out what is the length between the two depths. And so, you know, it's 3.8 here, and it's going to be decreasing to the normal depth, and we could find the length from where it's 3.8 until where it's 3.7, 3.6, 3.5, 3.4, and we could break it up into many, many different pieces. But the minimum number of pieces that we should break it up into is dictated by that 0.5 meter limit. That's the largest that those steps should be. And so let's start by classifying the water surface profile type, and then we'll take it from there. And by the way, you can do that on paper. You don't necessarily have to be working, and I did it on paper as well. The first 3 parts of the example you can do on paper, and in fact, even these ones on paper as well. But then when we get to calculating the length of the backwater, that's where we'll switch over to that template file that I gave you. So you can do goal-seek either. You can use goal-seek to calculate the normal depth, or maybe it's just better to calculate it by hand or using a calculator. So the critical depth should be 0.776. The normal depth is 1.195. And that tells us that this is an M1 profile at the location immediately upstream of the broad-crested weir. So if we go back to the picture here, actually not just at that location, but it's an M1 profile until the depth is no longer larger than the normal depth. So Yn is going to be greater than Yc the whole way. Just, the normal depth and the critical depth aren't going to be changing. But what will be changing along the length of the water surface profile is the actual measured depth. And back when the measured depth is equal to the normal depth, then it's no longer an M1 profile. At that point, it becomes uniform flow. But, so we know the critical depth, the normal depth, water surface profile is M1. So how many segments should be used? Anybody calculate that yet? 6? At least 6, yeah. Because if you do the calculations, we know the water depth is going from 3.8 until 1.195. And the most we can do is increments of 0.5. And so that means if we're going from 3.8 to 1.195, and each one of the steps can be up to 0.5 meters, then we should do 5.61 steps. And so that means that we'll use 6, because if we used 5, then each one of the changes in depth would be too big. So that means that each one of those steps is going to have a depth change of 0.43417. So 6 steps is actually what I had pictured here. Step 1 is from Y1 to Y2. Step 2 is from Y2 to Y3. So 1, 2, 3, 4, 5, 6. So there's going to be 6 segments. Now, the upstream and downstream depths for each of the segments is going to be, in other words, Y1 will be the normal depth. That's going to be the 1.195 that we calculated. Y7 is going to be 3.8. And before we do the method, we need to know each one of these depths that we're going to be trying to solve the delta L for. So let me give you a moment to calculate each one of those, Y1, Y2, all the way through Y7, based on each one of those being 0.434 meters. Yeah, it is. The only good thing about it is at least it's the same from institution to institution. So, like when I go to other schools, it's the same thing. All right, so direct step method. Nope. Cortana thought someone was going to use it. No. I'll show you. That's why there's some spaces here to begin with. Oh, was this in the spreadsheet that I already gave you? Oh, darn it. Oh. Let's pretend that was empty. Let's pretend that is empty and solve for it. All right, so this one is this minus 0.43417. Okay, there it is. And this is that minus 43417. Oops. Yeah. So what this is the this is using that step distance from the here we calculated how much we're going to step down in each increment. I don't want to short circuit any part of this example. So this is how much we're going to step down. I guess I could have it calculated here. I know I'm going from, let's do this. It's going from 3.8 to 1.195, and I'm going to do it in 6 steps. There's that number I need. All right, so this minus that. So the reason why it's that step distance is we're starting at the broad-crested weir where it's 3.8, and we're going to keep measuring until the water becomes the normal depth, which is 1.195. So that's the overall elevation of water difference, and we can only do it at 0.5 meter increments. So that it would mean 5.2 steps, but there's no such thing as 21% of a step, so we'll round it up to 6, which it's that same difference in water depth divided by 6 gives us that number. All right, so I did that here. This is how much we're going to be stepping down for each one of them. So then that minus this. And then if everything is correct, our final one should be equal to the normal depth. So let's cross our fingers that this minus that gets us back to the 1.195. Yeah, it's a relief that we're looking for. All right. So here's all of our starting parameters that we had. Now the cross-sectional area is for a rectangular channel, simply the width multiplied by the depth. So this is the cross-sectional area at any one of the locations that we've broken the segments up into. So I can carry that formula down through all the segments, and oh, I didn't anchor something. There it is. Let's try it again. And I don't need these zeros, so I'll delete those. Okay. Velocity, continuity equation, right? Q divided by A. And this time I will anchor it to begin with. So we've got a velocity for each one of those depths. And we got to make sure, does it make sense? Is it logical that the velocity is higher at the upstream section compared to the downstream section? Logan, why does that make sense?
Well, it's a very good question, but it just makes sense. I mean, honestly, I just thought it was kind of common sense.
No, I mean, okay, so here, upstream, don't help him out. He was yawning in my class. He's going to get a nodding and yawning. So they cancel each other out. I should leave you alone. Okay. All right, so thank you for admitting that. Let's look at the picture. All right. So that's all I wanted was for you to say you didn't understand. No. I'm just kidding. That's a joke. All right. It's the same flow rate. Now, this is non-uniform, but it is steady. Okay, so steady flow means that the flow rate isn't varying as a function of time. And so here, Q in equals Q out. Even though the depth is changing in the direction of flow, the flow rate itself is constant. So here it's deep. Here it's shallow. Where it's shallow, the water has to be moving faster to have the same Q as down here where it's deep, the velocity will be lower. So in other words, Q1, at section 1 I mean, Q1 equals Q7, where by Q7 I mean the flow rate at section 7, where we have some depth and some velocity. So we always want to do a reasonableness check as we're working through a spreadsheet, because it's easy to make a mistake. And so the fact that the velocity is higher here and lower there, that makes sense. We should not panic quite yet. All right, now for energy, we're going to solve for the energy at each one of those locations, just the depth plus the velocity head. Okay, so depth plus v squared divided by 2g. Okay, so we get our energy at each one of those sections. Now you may be wondering why we've got these spaces in between. And I won't leave you in suspense any longer. It's because we want to find the difference in energy between this section where the depth is 3.8 and where the depth is 3.366. In other words, this delta E is going to be the difference in energy between these two sections. And specifically, we want to know the energy at the upstream location minus the downstream location. And so that should be a negative value. So for delta E, make it the upstream minus the downstream. So you should get negative 0.43. Okay? And you can Control C and Control V, paste that formula everywhere you need it. The reason why we calculated the change in energy is, you know, the length of the profile is just how much energy difference there is between these two sections and the difference in the slopes. Now I got to point something out though. So we have a huge limitation in this method. Not only here I gave you the rules, so to speak, that we should work upstream if it's subcritical, downstream if it's supercritical, divide the reach into segments according to the limit of 0.5 meters. I didn't even maybe tell you the biggest problem of all is the channel geometry has to be the same upstream and downstream. This method doesn't account for the fact that what if the channel gets wider? Or what if it goes from at one section a rectangular channel and upstream maybe it's trapezoidal? Yeah, so you're thinking about the real world implications. It could be a long section as long as it was an engineered channel that didn't vary in width. But you're right that if we wanted to somehow apply this into like a natural channel, then we'd have to be pretty careful about applying it in sections where the width was about the same. And so if we saw that the width was changing, then we'd have to break this up into really small lengths, even smaller than this elevation limit would dictate. But fortunately, the method I'm going to teach you on Thursday allows us to have different channel geometries between steps. And so it kind of overcomes that limitation. But here for the direct step method, it should be from prismatic upstream to prismatic downstream, and it should be the same width, the same shape. All right, so now back to this. We found our delta E. Now the hydraulic radius in this case, all right, it is going to be the depth times 2 plus the channel width, right? That's the hydraulic radius of a rectangular channel. I almost stumped myself for a second there. Oh, what did I do wrong? Yeah, it's single, yeah, okay. So it is the width plus 2 times the depth. Okay, yeah. That's the wetted perimeter, yeah, okay. So we've got the wetted perimeter, and now we have to have the area divided by that. Thank you, yeah. I really did stump myself. All right, so hydraulic radius is the wetted perimeter. Now I'm going to do the area divided by that. There. All's well that ends well. I'm surprised I didn't have another column that had the wetted perimeter. But, all right, so we got the hydraulic radius. And again, we want it for each one of these sections. So I'll just copy the formula and paste it every place it's needed. And it's important to point out the difference between what's on a row and what's between a row. If it's on a row, those are the properties just at a single location. And so this is the hydraulic radius where the depth is 3.8. But then the delta E, which is between a row, that's how much energy difference there is between the sections. So certain things we can calculate at the location of interest, like the S sub F, that's going to be at this section right at the spot where the depth is 3.8. So we can rearrange Manning's equation to solve for the slope of the energy grade line when the depth is 3.8. So then that's what we're going to do here, is use this equation for the S sub F. Okay, so let me pause while you work on that, and I'll just circulate around and see if everybody's getting the right idea. Okay, so we use Manning's equation to find the slope of the energy grade line. The problem with having it centered is that then the formula gets pushed into the place where I want to click, and I can't click on it anymore. Oh, I could just type it in. Less risk of me making a mistake that way. All right, so I have the hydraulic, to the 2/3 power. Okay, and then square it all. All right, and we want to drag that formula through. I need to anchor the references to N and flow rate. Okay. Yeah? Ah, very clever. And it'll detect the pattern. That's a good suggestion. All right, and then the average, the reason why we're doing that is we want to find the slope of the energy grade line at the midpoint. So remember here in the formula, it's saying the segment length is the change in energy divided by the difference between the channel slope and the slope of the energy grade line at the midpoint. So we're trying to, once again, it's a curved surface, but we have to approximate it as a linear trend, and so we're at the very least, we're going to find the average energy grade line slope. And so be this plus that divided by 2. And then I'm going to highlight both of these, I guess. Or I don't know. All right, so we've got that and then the difference between the actual channel slope and the calculated average energy grade line slope. We can drag that through. So tell me, okay, so, oh, I take the first two and then drag it like that. Nice. That's going to save me time. It will. All right. And I'm even going to teach the 111 students that too, because they're learning for the first time to use Excel. So, all right, now delta E divided by this. And so it means that it's going to be 300 meters to go from point 3.8 upstream until we get to the point where the depth is 3.366. And I can highlight these two and then double click and add up all of the segment lengths, and overall it's going to be, now the negative means that you have to go upstream, opposite the direction of flow. So if we go 2.43 kilometers, then that's where we're going to get back to the normal depth. So it was asking this language the length of the backwater curve. So you should know, like when it says backwater, what that means is anytime you have an obstacle that's causing pooling, they call this the backwater. And it's something that you hear a lot in culvert analysis, because a culvert that isn't big enough will cause backwater, which means some degree of choking, and the depth is increasing as you have the obstacle there. And so in the opposite the direction of flow, the depth is decreasing. And so the length of the backwater curve is the length of each of the segments. And the shorter our elevation difference, the more accuracy we have. And so there's really no reason why we couldn't do, from 3.8 to 3.7, 3.6, 3.5. I mean, be kind of tedious, but I mean, once you type the formula in one time, then all you have to do is paste the formula through all the rest of the depths. So any questions about the direct step method? So you can include your calculations on Excel as part of your submissions for the homework assignment. But I think in the homework that it asks you to solve for the critical depth and the normal depth as well as a part of doing this. I think you're going to have to know whether it's supercritical or subcritical. Because remember, the rule is if it is subcritical, that's when you work upstream. So this is maybe one of the problems where you should do some of it on paper and then the rest of the calculations online. All right, that's all I have for you today. I'll see you Thursday. I haven't looked at your reports yet, so I'll say congratulations, hoping that it's something worth congratulating. But I assume just the fact that you're done with the project is a big relief, and so probably congratulations. I'll leave it at that. Yeah. Huh? Probably congratulations. That would be a good greeting card, wouldn't it?